3 days ago, a paper dropped in Nature Communications that, if it holds up, rewrites one of the most basic things we thought we knew about this planet, where our water came from. A team from ETH Zurich and Peking University figured out how to count hydrogen atoms inside iron under conditions that mimic Earth's core. And what they found is that buried 3,000 kilometers beneath your feet, locked inside molten iron at 5,000 degrees, there may be enough hydrogen to fill Earth's oceans 9 to 45 times over. Not as water, not as gas, as hydrogen atoms woven into nanostructures inside liquid metal, and some of it has probably been leaking upward for billions of years. But before we get to what that leaking might mean, and trust me, it connects to things you would not expect, we need to understand why this was so hard to figure out in the first place. Because the core has been keeping a secret, and the reason it kept it this long is almost as interesting as the secret itself. Here is the problem. We have never touched the core. We have never sampled it. The deepest hole humans have ever drilled is the Kola Super Deep borehole in Russia, 12.3 kilometers. That is impressive until you realize the core-mantle boundary sits at 2,900 kilometers down. We have scratched less than 0.5% of the way there. Everything we know about the core comes from earthquake waves, from math, and from lab experiments that try to recreate what is happening down there. And one thing those earthquake waves have been telling us for decades is that the core is weird. It is mostly iron. Everyone agrees on that. But pure iron at those pressures would be denser than what we actually measure. Something lighter is mixed in, nickel, sure, but also other stuff, silicon, oxygen, sulfur, and potentially hydrogen. Hydrogen has always been the suspect that nobody could pin down. It is the lightest element in the universe, the smallest atom there is. It slips through instruments the way it slips through metal lattices. One expert literally called it a slippery element in experiments because it diffuses so easily you can barely catch it. And previous attempts to estimate how much hydrogen lives in the core produced numbers that were, frankly, all over the place. We are talking a range from about a tenth of one ocean to more than 120 oceans. That is a spread of over 1,000 times. Not great. The old method was basically this. Take some iron, add hydrogen under pressure, then measure how much the iron's crystal structure expands using X-ray diffraction. From the expansion, you infer how much hydrogen went in. The issue is that hydrogen is so small and so light that interpreting those expansions was wildly ambiguous. Different labs, different assumptions, different answers. So here is what this new team did differently. And this is where it gets genuinely clever. They took a tiny piece of metallic iron, embedded it in a water-bearing crystal capsule, and squeezed it between two gem-quality diamond tips in what is called a diamond anvil cell. These diamond tips are a tenth of a millimeter across. Then they fired a laser through the diamonds and heated the sample to about 5,100 Kelvin. That is roughly 4,800 degrees Celsius, nearly as hot as the surface of the sun. And the pressure, 111 gigapascals. That is about 1.1 million atmospheres. Essentially, they recreated the conditions of Earth's core formation in a space smaller than a grain of sand. Under those conditions, the sample completely melted. Iron, silicon, oxygen, and hydrogen all mixed together in a liquid state, mimicking what the early Earth looked like when it was essentially one giant magma ocean, and the core was forming by sinking iron pulling lighter elements down with it. Then they did something critical. They quenched it. Flash-cooled the sample to freeze the atomic arrangement in place, like taking a snapshot of what was happening inside the liquid metal at the moment everything was molten together. And then came the really remarkable part. They carved this recovered sample into a needle with a tip 20 nanometers wide. To put that in perspective, a human hair is about 80,000 nanometers across. This needle was 4,000 times thinner than a hair. They placed it under extremely high voltage, and one by one atoms were ripped off the surface of that needle and flung toward a detector. Each atom's identity, each atom's position in three-dimensional space, recorded. This technique is called atom probe tomography, and it gave them something no one had before: a three-dimensional atomic map of what hydrogen actually does inside iron under core-like conditions. And what they found changed the picture. Hydrogen does not just float around freely in the iron. It bonds with silicon and oxygen into tiny nanostructures embedded within the metal. These clusters are less than 200 nanometers across, and within those clusters, the ratio of silicon atoms to hydrogen atoms was roughly 1 to 1. Hydrogen was present at over 30 atomic percent inside these structures. That is not background noise. That is not contamination. That is a massive signal. Now here is why that 1 to 1 ratio matters so much. Previous geophysical studies had already established that Earth's core contains somewhere between 2 and 10% silicon by weight. That number is relatively well constrained compared to hydrogen. So if silicon and hydrogen show up in equal atomic proportions in these nanostructures, and if that ratio holds for the real core, then you can use the silicon as a ruler to measure the otherwise invisible hydrogen. You use what you can see to count what you cannot. Do the math, and you get 0.07 to 0.36 weight% hydrogen in the core. Translate that into something a human brain can actually grasp, and you get 9 to 45 oceans worth of water equivalent. The low end alone, 9 oceans, is already extraordinary, and that is the conservative estimate. Some scientists actually think it could be even higher. Kei Hiroshi from the University of Tokyo, who was not involved in this study, pointed out that his own previous work estimated core hydrogen at 0.2 to 0.6 weight%, which is more than this new paper proposes. His concern is that when you depressurize the diamond anvil cell to recover the sample, some hydrogen inevitably escapes. That loss was not accounted for in the new paper's calculations. So if anything, the real number might be higher than 45 oceans, not lower, which is a fascinating kind of criticism. The skeptics are not saying the number's too big. They are saying it might be too small. But let us be honest about the weaknesses too, because this is how science actually works. The central finding, the nanostructure with the 1 to 1 silicon to hydrogen ratio that comes from a very small number of successful atom probe samples. These atom probe needles are incredibly fragile. They fracture constantly during the measurement process. The team had a high failure rate, and the key statistical data for the main nanostructure came from a limited number of successful runs. That is not automatically a deal breaker, but it is something that needs to be reproduced. Also, and the peer reviewers flagged this explicitly, the paper reduces certain assumptions that plagued earlier work but introduces others. For instance, it assumes that the nanostructures observed in the quenched sample accurately reflect what exists in the actual liquid core. But the quenching process itself might change the distribution of atoms. You are extrapolating from a nanometer scale sample to a core 3,486 kilometers in radius. That is a gigantic conceptual leap, and the silicon to hydrogen ratio of about 1 to 1 is the foundation of the entire estimate. If that ratio is even slightly different under true core conditions, the number of oceans shifts substantially. The range of 9 to 45 already reflects a 5-fold uncertainty, mostly coming from how much silicon the core actually contains. So this is not settled science. This is a strong new data point from a genuinely novel method. The peer reviewers praised the innovation. External scientists like Hilke Schlichting at UCLA said it really changes how we think about where our water comes from. But everyone agrees more work is needed. Now, with all that context, let us talk about what this actually means if it is right, because the implications go in directions you might not expect. The standard story about Earth's water goes something like this. Earth formed close to the sun, too close for water to condense during the early solar system. So the planet started out dry, a barren rock. Then later, comets and water-rich asteroids bombarded the surface and delivered the oceans we swim in today. Water arrived from the outside, like a cosmic delivery service. This new finding says that story is probably wrong, or at least incomplete. If 9 to 45 oceans worth of hydrogen were already getting pulled into the forming core during the first million years of Earth's existence, then the planet was not dry at the start. It was wet from birth. The hydrogen was there during the main stages of accretion, sourced from the protoplanetary disk of gas and dust that formed the solar system. It got incorporated into the iron as the core was separating from the mantle in that primordial magma ocean. The lead author, Dongyang Huang, put it directly. Earth's core would store most of the water in the first million years of Earth's history. The mantle and crust come next. The surface, where life resides, contains the least. Think about that for a second. The Pacific Ocean, the Atlantic, the Indian, the Arctic, all the water on every continent, every cloud in the atmosphere. That might be the smallest fraction of Earth's total hydrogen budget. The scraps, the leftovers that did not get swallowed by the core. One of the co-authors from ETH Zurich, Motohiko Murakami, said the water we see on Earth's surface today may be just the visible tip of a gigantic iceberg deep inside the planet. And this is not even the first clue that the deep Earth is wetter than we thought. In 2014, a geologist named Graham Pearson found a tiny piece of a mineral called ringwoodite inside a diamond that was brought up from about 525 kilometers deep by a violent volcanic eruption in Brazil. That diamond had been bought from artisan miners for about $20. It looked like it had been to hell and back, but inside it was the only terrestrial sample of ringwoodite ever found, a mineral previously only seen in meteorites and lab experiments. And that ringwoodite contained 1.5% water by weight, locked in its crystal structure. If representative of the mantle transition zone between 410 and 660 kilometers deep, that layer alone could hold 1 to 3 oceans of water, equivalent. So now you have the mantle transition zone potentially holding a few oceans, and below that, the core potentially holding 9 to 45. The deep Earth is not the dry, dead zone we imagined. It is soaked. But there is a second implication, and this one is arguably even bigger. Earth's core is what generates our magnetic field. The outer core is liquid iron, and convection currents in that liquid iron create what is called the geodynamo. That geodynamo produces the magnetic field that wraps around the entire planet and shields us from the solar wind. Without it, charged particles from the sun would strip away our atmosphere over time. No atmosphere means no liquid water on the surface. No liquid water means no life, at least not life as we know it. The question of what powers that convection, what keeps the liquid iron churning, has been one of the big puzzles in geophysics. And the new paper offers a piece of that puzzle. As the core slowly cools over billions of years, hydrogen along with silicon and oxygen would begin to crystallize out of the liquid iron. This crystallization creates what is called compositional buoyancy. Lighter material rises, heavier material sinks, and that drives convection. Dongyang Huang explicitly connected this to the magnetic field, saying this crystallization would provide a driving force for an ancient geodynamo, which he called indispensable for developing Earth into a habitable place. So follow the chain. Hydrogen gets incorporated into the core during formation. Over billions of years, that hydrogen helps drive the convection that generates the magnetic field. The magnetic field protects the atmosphere. The atmosphere keeps water liquid on the surface. And that liquid water is where life evolves. The very element that sank into the deepest part of the planet might be part of what made the surface livable. Now let us talk about the leaking, because that is where this connects to something we can actually observe. Murakami states that over geologic time, some of the hydrogen has probably leaked from the core into the mantle. When hydrogen reaches the oxygen-rich mantle, it reacts to form water. And that water, even in small amounts, makes mantle rocks dramatically easier to melt. Lower melting point means more magma. More magma means more volcanic eruptions at the surface. So there is a chain running from the core to the volcanoes. Core hydrogen leaks to the mantle, becomes water, lowers the melting point of rock, generates magma, and fuels eruptions. Now, important caveat, this is not some crack in the earth with hydrogen streaming out. It is an incredibly slow geochemical process happening over billions of years, probably limited by diffusion, and the total flux might be small. The paper frames it as a possible mechanism, not a measured present-day flow. So when you hear leaking, think glacial timescales. Think the slowest drip you can possibly imagine. But even a slow drip over 4.5 billion years adds up to something. And this idea is not coming out of nowhere. In 2022, geophysicist Peter Olson and geochemist Zachary Sharp at the University of New Mexico modeled the movement of helium-3 leaking from Earth's core. Helium-3 is a primordial isotope formed in the aftermath of the Big Bang. They found it escaping from the core at a rate of about 4 pounds per year through the mid-ocean ridge system. Olson actually suggested at the time that nebular hydrogen leaking from the core was something that could be usefully investigated. This new paper is essentially doing exactly that. Then in May of 2025, a team from the University of Göttingen found direct isotopic proof that the core is leaking gold, platinum, and ruthenium up through mantle plumes to the surface. They found an isotopic signature of ruthenium-100 in Hawaiian volcanic rocks that could only have come from the core. First direct proof that core material is reaching the surface. And in November 2023, researchers published evidence of what they call the E-prime layer, a hydrogen-rich, silicon-depleted zone sitting right on top of the outer core, formed by water from subducting tectonic plates trickling all the way down to the core-mantle boundary and reacting with the liquid iron there. So the picture that is emerging is that the core-mantle boundary, this zone 2,900 kilometers below us, that was long thought to be a sharp, impermeable wall, is not impermeable at all. Material is going down. Material is coming up. Hydrogen, helium, gold, platinum. There is a slow but real chemical conversation happening between the core and the mantle. A geodynamicist at Brown University, Harriet Lau, summed it up when talking about this broader picture. She said, "This is kind of crazy. If material is effusing from the core into the mantle, is the boundary between them as distinct as we think?" Good question. Now there is one more angle here that deserves attention, and it is the one that extends this story beyond Earth entirely. If hydrogen incorporation into the core is just what naturally happens when a rocky planet forms from a hydrogen-rich protoplanetary disk, then this is not unique to Earth. Mars could have a hydrogen-rich core, Venus could, Mercury, and any rocky exoplanet that formed under similar conditions. In fact, the same week this hydrogen paper came out, another team at ETH Zurich published a separate paper in Nature Astronomy about what they call the chemical Goldilocks zone. They found that only planets with exactly the right amount of oxygen during core formation end up with enough phosphorus and nitrogen in the mantle to support life. A little more or less oxygen, and the essential elements get locked away in the core or distributed wrong. Put these two papers together, and the core is not just a ball of hot iron sitting at the bottom of the planet doing nothing. It is the hidden architect of surface habitability. It controls the water supply by sequestering hydrogen. It controls the magnetic field through convection. It controls the availability of life-essential elements through its chemistry during formation. The conditions at the center determine whether the surface would be a living world or a dead rock. We've sent robots to Mars. We've photographed a black hole 55 million light-years away. We've mapped the cosmic microwave background from the birth of the universe. But the most mysterious place we know of might be directly under our feet. A ball of liquid iron the size of Mars, 3,000 kilometers down, holding decades worth of unanswered questions and apparently 45 oceans worth of hydrogen that we only just learned how to see. The glass of water sitting on your desk right now, the hydrogen atoms in it. Some of those may have spent the first few billion years of Earth's history locked in the core, leaked slowly into the mantle, reacted with oxygen, rose through volcanic systems, evaporated into clouds, fell as rain, and ended up in your cup. A 4 billion year journey from the center of the Earth to your lips. Or maybe not. Maybe those particular atoms came from a comet. That is the thing. We are still figuring it out. Want more of the latest science that rewrites what we thought we knew? There is always another discovery waiting.